Okay. Everybody is able to see my screen?
Yes, you can see the screen.
Okay. So let me just set up my screen a bit. Okay. So, kia ora everyone. I'm Satwinder Singh, last year PhD student at Massey University, Auckland, New Zealand. So I'm doing my PhD under supervision of Professor Willie Wang. So today I'm going to talk about automatic speech recognition for low resource languages. This is kind of my research objective of my PhD thesis. So we'll talk about that. So uh, today I'll introduce some of the basics concepts of speech recognition and especially related to low resource languages. I'll also present some of the challenges of this research area, and then I'll go through some of the solution proposed to alleviate this issue of lower source languages. And lastly, I'll go through some of the work progress and some of the results that we have achieved so far in terms of Māori language and some results presented in Punjabi language. So before beginning, so what is the speech recognition? So speech recognition, or simply a speech recognition, is a process of accurately translating the spoken utterances to their corresponding word sequences. So it's a widely researched area, and there are a lot of application of speech recognition. So for example, they have been used in intelligent assistants, uh, making captions to audio and videos. So I mean, there are a lot of applications of speech recognition in various domains of applications. So what is involved in a speech recognizer at highest level is fairly straightforward, and nothing has really changed from very long time back. So there are sort of three components in speech recognizer. The acoustic model typically deals with the raw audio waveform or other audio features, just like MFCCs or MEL spectrogram or spectrograms, and then predict the phoneme for each waveform corresponding to their characters or subword levels. And the second component is a lexicon or pronunciation dictionary, and it deals with how to say something. Say, for example, there is a word cat, and in computer language, it can be pronounced as cat. So pronunciation models sort of deals with these kind of stuff. And the last component is a language model that sort of says how likely is that something is correct sentence. So if the sentence is well formed, then it is most likely they have achieved, better scores, and as compared to sentence which has some non-verbal communication in it. So the overall goal in traditional system was to, collaborate all those components and then get the output for these output for the, audio. But these systems were very hard to optimize, and they have a lot of issues in optimizing all three different models. So to ease up the process, the researchers has presented the end-to-end system where the probabilistic model, which are based on deep learning models. So these try to learn jointly all these components together, and then they produce the output transcriptions. So these are very fairly simple model as compared to the traditional systems. So now what are the low resource languages? So there are many definitions to low resource languages. So what we are defining here is from the perspective of speech recognition. So the languages that do not have enough linguistic resources needed for building ASR systems are considered as low resource languages. So these linguistic resources include paired speech corpus, which means speech utterances and their corresponding labels, and lexicon or pronunciation dictionaries, and huge amount of unpaired text for language modeling. So we have over like 7,000 languages around the world, but only 100 languages approximately have a matured ASR system. So the reason being that they don't have an matured system for the most of the languages is that these languages don't have enough speech resources, linguistic resources needed for building the system. So here is a relationship. This figure represents the relationship between word error rate, which is the common matrices used for speech recognition tasks. So relationship between accuracy and the amount of data available. So if we talk about the amount of ASR back in 1970s and until 2010, which are the system based on Gaussian mixture model or HMM models. So these, if you increase the data in terms of hours, the word error rate, slowly get down, but it is not very significant. However, if you compare the systems that are developed after 2010, which are usually based on deep learning neural network models, so they have impacted hugely with the availability of data. So more the data is, and then we have a lower the error rate. So lower is the better here. So if you increase the data, you will have a better results in terms of word error rate. So there are many challenges presented while we are developing, the low resource system for ASR applications. So the biggest challenges for building ASR system for low resource language is scarcity of labeled data. We have a data, but we don't have a labeled data. So labeled data is very important here. So this could be attributed to the amount of diverse speaker present in a language. For example, many languages have relatively few native speakers, and for these languages, it's very hard to acquire speech data. Further, the data labeling process is extremely time consuming, and it is very costly process. So manual labeling is very, time consuming process. For other resources like lexicon, so some languages don't have enough research and enough people working in that area of research. So they don't really have a linguistic expert to create pronunciation dictionaries and other linguistic resources needed for that building ASR system. So to deal with these kind of problems, so there are many solutions proposed in the past. So these include multilingual systems, cross-lingual transfer learning system, meta learning system, and semi-supervised learning system. And there are some data augmentation techniques as well. So we will discuss these detail in further slides. So the first kind of systems are multilingual system. As name suggests, these systems are very interesting idea and have trained the model on multiple languages. So more than one languages has been used for training a system. So we have audio features, and then we have hidden layers. So each language share the hidden layers, and they have their independent output layers, which is called softmax layer. So in detail, like in deep neural network, shared hidden layer model proposed by Huang et al. In 2013, they argue that deep learning network model, the hidden layer can be considered as increasingly complex feature transformation layers. So if you see, these layers are, these many hidden layers are considered as complex feature transformation. And the final softmax layer considered as log linear classification layer. So while log linear classification should be different for different language, feature transformation layers can be shared across many languages. So these can be, hidden layers can be shared among many languages. And then these languages share some common phone structure and other linguistic resources. And then a language independent layer like softmax layer is used for each different language. And with these languages, they have presented the results. So here you can see that shared hidden layer multilingual deep neural network can reduce error by 3 to 5% relatively for all languages using shared model. So here you can see we have data from 4 different languages, French, German, Spanish, and Italian. So we have like 40K for French language, and 37K for German, and 18K for, this is fairly very low data. And Italian language has 31K sentences. Compared to monolingual DNN system, we achieve like 3 to 5% of improvement, or you can say word error rate reduction compared to monolingual systems. So it fairly improves the system compared to the only one language used for training a system. Another set of algorithms are very similar to what we have just saw. The only difference is they have used LSTM network, which is long short-term memory model, recurrent models. So instead of DNN, they have used LSTM because LSTM tend to have a longer context dependency. So they tend to work well on sequence data. So and one more thing here to be noted, that LSTM, usually kind of have a problem with vanishing gradient. So to resolve that problem, they introduce residual learning in between these LSTM layers. So they have proposed their results on many languages, including Mandarin, English, Japanese, Arabic, German, and Spanish languages. And these languages training data ranges from 13 hours to 16 hours, and testing data is around 1 to 2 hours data only. So if you compare the result of these models, so the above column, above set of rows represents the vanilla multilingual LSTM network, and the later represent the same model but with the residual connection. So here you can see that the very best model with 4-layer in classical model represents only 51% of word error rate, as compared to the residual network, which achieves 49.61 with 6 layers. So residual connection indeed improves the performance on many layers, and if you have many layers of dependency of when you want to capture context in the language. And another set of multilingual systems has been proposed in terms of transformers. So the model that we just discussed, they have some problems, like they need some lexicon and pronunciation dictionaries. But as we are talking about low resource languages, we don't really have for some languages, we don't really have these kind of resources. So Zhao et al. Present SHL, which is shared hidden layer model with transformer, which alleviate the problem of having linguistic resources. So this is a sequence to sequence based transformer model, and they not only reduce the linguistic dependency on the model, but also improve the word error rate. So we can see the results here. So they compare the previously discussed DNN model with their mono and multilingual versions, and as you can see that they have improved on the similar set of languages, uh, you know with the best residual LSTM network. They have achieved 50.25 word error rate, but as compared to multilingual transfer end-to-end models, they have achieved 45.65. So there is absolute 5% of around 5% of word error rate reduction. So here we can conclude that the end-to-end sequence to sequence model have better learning capabilities as compared to the traditional model, which requires more linguistic resources as compared to the transformer model, which are recent and have encoder decoder structure, which can learn from little data. And the next set of algorithm are based on cross-lingual transfer learning. So the motivation here comes from the way human acquire new knowledge. So humans have an inherent ability to transfer knowledge across tasks. So what we acquire as a knowledge while learning about one task, we can utilize in the same way to solve the related task. So here you can see we have one data set which is fairly big, and we learn the system on that data set. And the second data set, the actual problem that we are working on, is fairly small, and we transfer that knowledge from that system to the second system, and then we get the better results. So that's how transfer learning in general works. So on top of that, like the transfer learning can be divided into two types. One is transferring bottleneck features, and another one is transferring the models parameters. So we'll discuss each one in next slide. So transferring the bottleneck features. So in transfer learning, we take pre-trained model and then remove the output layer. So, and then construct our own in place of it. So doing so, it will remove the pre-trained weights at those layers. So now the original network before the output layer is frozen so that when the training starts on the new data set, only the newly added output layer are trained. Here, the input to the output layer is the bottleneck feature. So bottleneck features contains only few nodes compared to the previous layers, and it can be used to obtain a representation of input with the reduced dimensionality. So bottleneck feature is just like, as we extract MFCCs or filter banks from the raw audio signals. So we use the bottleneck feature as an input to the other layers that we are transferring our knowledge to. So these are the bottleneck features. And another class of transfer learning present the transferring of models parameters. So here the architecture of cross-lingual model knowledge transfer learning method. So on the left side, the model is shared hidden layer, which refers to as source model, and the right hand side model presented as a target model. So the shared parameter of shared hidden land more are transferred to the target model. So here we have two languages in the source model, language 1 and language 2, and they have shared hidden layers, BLSTM, which is bidirectional LSTM layers. So we share these layers to the target model, and then the target model have their own feature transformation layers, and then they have their own independent softmax layer. So in this case, we just transferring the already learned knowledge to the new target model. So in this case, we can achieve better result even with the few hours of data. So that's the kind of goal of transfer learning. You're learning from the fewer amount of data. So here are the results presented with the such models. So in the source models, we have 12 language that they have used, and the languages data ranges from 40 hours to 70 hours each language in full language pack. And for the target languages, they include three languages, which are Pashto, Turkish, and Vietnamese. And the data include approximately 77 to 88 hours of language in full language pack. And if we talk about the test set, we have data around 10 hours for each language, similar to limited language pack. So here results, we can see that with no transfer learning, the results are around 56 to 57 on LLP, which is limited language pack. And on full language pack, it is between 45 to 48. And if you compare with the uh, retraining on, transferring the knowledge from 12 source languages, the results improvements are there. So there are absolute 3%, around 3% in Pashto and Turkish, and around 2% in Vietnamese in a limited language pack. And similar result has been achieved in full language pack. So here we can also analyze that full language pack has around 40 to 70 hours of data. Uh, that's the reason that it is performing good as compared to the limited language pack, which has only 10 hours of data. So indeed, cross-lingual transfer learning improves the low resource speech recognition performance. And another class of algorithms are meta-learning algorithms. So meta-learning algorithms. So basically the motivation comes from, again, human learning. So in a deep learning, algorithms tend to work well on the task having huge amount of training samples. The basic reason is that the deep learning model, as it gets deeper and deeper, they have millions of parameters to optimize. So the random initialization of parameter requires a model to look into more data to reach to an optimal solution using gradient minimization process. So that's the reason the models which have a more data, they tend to perform well, as compared to the model who have a limited data, they tend to perform worse. However, this is not like l- the way human learns. So we do not require large number of samples or large number of examples to learn from, the data. For example, here we have number of instruments. So if you saw one instrument or two instrument and three instrument, you can easily figure out that the other instruments. It's kind of how human brain works. So say, for example, if you learn drums or guitar or saxophone or piano, you can easily transfer the learnings to learning a new instrument, say, for example, a flute, because they have similar sort of chord structure and other things. So we tend to transfer knowledge between already learned experiences to the new task. So this is how meta learning works in general. So this is the actual formulation of meta learning. So in general, meta learning, also known as learning to learn approach, which focus on improving the learning efficiency of the model based on previous experience on wide variety of tasks. But these tasks are very similar tasks, not very, hugely different tasks. So in meta learning, we have a meta train set, which is set of related training sets, and meta test set, which has their corresponding test sets. So it is a bit confusing if you see. So meta train has a different training sets. So it's not like in usual training, we have examples in training set. So here in meta train, we have data sets of different data sets instead of examples. So these different data sets have a different examples to them. And similarly, we have test set. So test set also have their corresponding test set compared to the meta train set. And these in meta training, the meta train set is also called as sport sets, and the meta test sets also uh, called as a query sets. So in the objective is to get the uh, most educated, guess around the parameters, so that we can easily adapt the parameters to new tasks. We can easily, use our previous experience to the learning to the new task. So this is the formulation. And in meta learning, the famous model which was proposed by Finn et al. In 2007, it is called model agnostic meta learning. So in this meta learning class of algorithms, the learning is done on two levels. So one level is inner loop, where model acquires task specific knowledge, whereas the second level, which is outer loop, facilitate tasks across learning. So this is very famous gradient based meta learning approach. So here is a flow chart of the algorithm. So initially we have a sports set examples, and then we have parameters. Let me just use my laser pen. Okay. So we have a sports set, and then we have a random initialized parameters, and then we have internal base model. So in our case, we have ASR system here, and then we we use those initial parameters, and then we make predictions on sports set. And then we calculate the loss, and then we update the internal parameters of the model, which is ASR in our case. And then we do this for n steps. So n is not very large. So it is around 5 or 10, depending upon the application that we are doing. So here we have only 5 steps, say, for example. So after 5 steps, we acquire a meta model, which is having a theta n parameters. So theta n means after n step, we achieve one initialization of parameters, which are theta n. And then we use those parameters on our uh, test set, which is xt, with those learned uh, theta n parameters. And then we again repeat the process of calculating a loss, and then we update the meta parameters in auto loops. And then these parameters again initialize, and then these are again used as initialization. So this way, model can acquire a very good guess, like what sort of initialization should be done so that our model can fine tune on a different tasks with very few examples as well as very few epochs. Okay. So these are the results with respect to low resource languages. So this is the paper which is presented by HSU. So it represents the character error rate. So they have compared the model with no pre-training, multilingual training, and meta training. So they have used 6 languages as their source languages, and then they have 4 training as their target training languages. So in first set of training, as you can see, with no pre-training, the results are very poor. So it's very high character error rate. And with the pre-training with the Bengali, Tagalog, and Zulu language, which are present in Babel dataset, they achieve fairly good result as compared to multi as well as no pre-training. And this kind of same for every language. So it improves the performance on multilingual as compared to the meta training. And here in the third set, they combine both the set. And here you can see it's a very, uh, we tend to think that if we add more and more languages, our system could improve the performance, but it totally depends upon the type of algorithm we are using and type of the languages we are using. Say, for example, if the languages are not very phonetically similar, then they will not produce good results. But if the languages are phonetically similar, say, for example, a Maori language that we are working on is pretty and fairly similar to Japanese language. They share some phones. So if we pre-train on Japanese and then fine tune on Maori, then it could produce very good results. So in similar fashion, that if we use different languages, our result can get worse. So here you can see that if you use 6 languages instead of 3, the results are not improving, but they have like 1% increase in in character error rate. So the languages must be chosen intelligently. So it can be based on phonetic similarity, language family similarity, or it can be geographic area or dialects and whatever parameters are there. And the next set of algorithm that we are talking about are the semi-supervised learning algorithm. So the semi-supervised learning algorithms, they're trained on unlabeled data in unsupervised fashion and fine-tuned using fraction of labeled data. So we have millions of unpaired audio. So we train the model on unpaired data, and then we use very few hours, even few minutes of labeled data to fine-tune our model. So this class of algorithm, there is famous word-to-vec model, so which is presented by Facebook. So it's very powerful self-learning model. So the idea is kind of taken again from human learning. Say, for example, it is like child that first learn to listen and then learn to write. So here, learn to listen correspond to pre-training on unlabeled data, and learn to write is like fine-tuning on target language. So here you can see we have raw audio, and then we have some feature extraction CNN layers, and then these are fed to transformer network, and then there is a quantization module. So quantization module is nothing, it just discretizing the latent space features, and then again they fed into later stage to constructive loss, constructive loss, so that we can get a learning process. And then there is another important factor to note here. So transfer model here use the masking process. So masking is nothing, it's just like, filling in the blanks. So in latent space, the transformer tend to mask some of the input so that the model tries to predict what sort of mask should be there. So say, for example, if there is a sentence called today is dash day. So on the contextual representation based learning, So it should be, the model should acquire knowledge, should it be hot, good, or whatever the model is. So it tries to learn how to fill in the blanks using wave to wave model, using masking. And so on the basis of that, they have also presented some model which is especially created for low resource languages. So these are class of models called XLSR models. So everything is same, only XLR learns a single set of quantized latent speech representation which are shared across languages. So these are the latent space quantized representations. So all the languages share the similar phones by which they learn from different languages. So the largest model they have presented is trained on as large as 53 languages. And they have presented their result, which are very good. So they have used, again, Babel data set. There are many languages, including, Yulu, Bengali, Telugu, and many other languages. And they have used common voice data set as well, which has very crowdsourced data set languages. So as you can see, compared to a monolingual and training from scratch, the XLR system, which are pre-trained on 53 languages and fine-tuned on single languages, produce very good results. So the gains are very good because as compared to 47, they achieve 24 on Bengali, and the trend is same for rest of the languages. So these semi-supervised learning approaches fairly improves the performance in low resource settings. And another clever approach which is used for low resource language to get more out of it, the data augmentation techniques. So data augmentation is used to increase the amount of data just by adding slightly modified copies of already existing data or newly created synthetic data from existing data. So it sort of act as a regularizer in the network and helps reduce overfitting while training a learning model. And eventually, if you reduce overfitting and you increase the data, eventually it is obvious that your model will generalize well on the data, and you know gives better results. And there are many existing approaches in the data augmentation field. So we'll not talk about in detail. It's just like, there are many algorithms. So for example, there is speed and pitch adjustments. So in this case, in speech perturbations, we increase the speed of the speech signal to make more copies of it. And then in pitch, we adjust the pitch. In additive noise, we just add noise so that a model can be more noise robust and have more generalized accuracy. And then there are some other algorithm which based on warping a signal, which, for example, there is a vocal track length perturbation. And then there are spec augments. So spec augment was proposed to mask the MEL spectrogram along the time and frequency axes and achieve good improvement on speech recognition. And recently, very recently, actually, mixed speech has been proposed. So mixed speech use two different type of features, say, for example, MFCCs and MEL spectrograms together to make more examples of the data so that we can, alleviate the problem of overfitting and increase the accuracy of the model. And also we have wave augment, which also have a very collection of a different combination of speed, pitch adjustment, and noise, and different other techniques and effects like reverberations to increase the data. And the lastly, we have speech synthesis. It just like, producing synthetic speech from the text data set. So it's a very fairly simple idea, but you have to have enough data just to train your text to speech model so that it can generate good quality of speech synthesis data. And here I will present some of the initial work that we are doing at our lab. So our results are based on data set which have been used, we've been using from TBN's news broadcasting data set. So this data set is having data around 11 hours, which are 5,355 sentences in total. And the duration lies from 1 second to 20 seconds. So we design a 6:2 ratio random split. So 60% for training, 20% for validation, and 20% for testing. And this is how our data looks like in raw form. So this is labels for the text, and this is a path for the audios. So we use that structure while we are training the model. So our model is based on the XLR model that we just discussed. So that model is previously trained on 53 languages. We just fine tune on the Māori language dataset that we have here. And on the basis of that, we present our result with the 5-fold cross validations. Each fold is very consistent here, but the scores that matters are the average score. So we achieve average score of 21.9% word error rate on Māori speech data on test set. And similarly, we achieve 8.87 correct error rate. So here, we also experimented with the extremely limited data. So here we train a model, fine tune the model on 10 minutes of data. So with the 10 minutes, it fairly achieves around 40% of word error rate and 12% of corrector error rate. And if we increase data to 1 hour, we achieve 34 and 11, and 2 hours present a very good result, which is around 23%, and corrector rate is around 8%. And if we use all data, we achieve fairly similar result to what we have achieved with the 2 hours of data. So the results are not improving drastically. As you can see, corrector error rate worsen with the 6 hours of data. So this could be attributed to the speech style that we have collected in Māori news broadcasting data set. Because as I remember, while I was labeling, so this data was very, you know, it's a written speech, read speech data set. So they have script and they read the news. And we don't have a very diverse number of speaker in this data set. So if we add more diverse data to our data sets, so it can improve the performance further using few hours of data. And further, we also augment our Māori speech data set with wave augment we just discussed. It just presents some combination of pitch modification, noise, and other effects. So with data augmentation, it indeed improved the performance in limited data situation as well as in the full data augmentation, full data, which is around 6 hours. So we achieves eventually we achieves 20%, around 20% of word error rate and 8% of corrector error rate on Māori language with wave data augmentation. So this is the preliminary result with the Māori language. And with the Punjabi language, so Punjabi is my native language. So even though Punjabi language is widely spoken across the world, so we have like 100 million plus speakers, but still we don't really have a paired speech data corpus and other linguistic resources. So we use, common voice dataset, which is presented by Mozilla. So the common voice datasets are crowdsourced data set. So people record their voices with the prompted sentences online, and they compile the data set. So here we have only 1 hour of speech data for Punjabi language. And to augment the data, we also synthesize our data set. So we had Punjabi text to speech models. So we have huge collection of Punjabi unpaired text. So we use that unpaired text, and then we synthesize around 23 gigabytes of Punjabi sentences, speech data. and then we presented the data according, while training the model. So we train the model on synthesized data and as well as on Common Voice version 7 data set as well. So on training on the same set and testing on the test set of the synthesized set using XLR53 model, we achieve very good result, which are like 2% character error rate and 8% of word error rate. But the synthesized result alone are not very significant because the data set model has very, monotonic voice, because it is not a natural voice. So the model that we have generated has only one female voice. So the model that we have just trained is very speaker independent with just one speaker. So we can prove that, like, we train the model on synthesized model, and then we test the model on Common Voice test set. So here you can see that performance, our model failed to generalize the, uh, uh, test results on Common Voice test set. So here we can see that the speech recognition really needs a diverse speakers so that it can generalize to different data set. So we also tested our model on Common Voice train set and Common Voice test set, and we achieve 20% of character error rate and 61% of word error rate. And then we improve the Common Voice data set using synthesized data set. So we use this trained data set and then double fine tune with the Common Voice trained set. And then we achieve absolute 3% of improvement in character error rate and a huge 10% of improvement in word error rate. So here we can say that our synthesized data indirectly improve the performance of the model if we pre-train on synthesized data and retrain it on other data set and then test on their own test sets, and then it can improve the model's accuracy. So that's it. Any questions?
So I had a number of questions. Can you hear me?
Yes, I can.
So when you were selecting from the 53 languages, I was wondering if there's a way of automatically converging on what subset of those languages could be retained with fine tuning. So for example, if you were trying to train something to recognize, say, Tagalog, right?
Mm-hmm.
You might be well advised to retain, I don't know, Māori, Japanese, and Spanish, but not,
Mm-hmm.
say, Thai. So could you automatically converge on a, not just fine tune on a particular language, but fine tune on a subset of language with final fine tuning on the particular language?
I think in their paper, they have explained that they have used multiple data sets. So they have also presented the results without the languages that are not seen in the pre-training, but they just, seen in the fine-tuning phase. So they are not using any automatic. It's just like, they train the model with the 53 languages, and then you can fine-tune any language that you have.
Right. So I'm suggesting sort of a modification of that, where you don't just fine tune to a particular set, right? But you fine tune to a subset of the languages, which are automatically chosen to be consistent with the target language. So for example, if you're fine tuning for Māori, you might want to automatically find that if you retain Tagalog and Spanish and Japanese, right? And with a particular weighting across the samples from that, you might do significantly better. So
Yes,
it's just a thought. Yeah. The other thought that I had when you were talking about your work with Punjabi is to wonder whether or not, as well as using synthesis, you could use, so if you don't have, for example, a large amount of written data in Punjabi, one could imagine using translated synthesis. So start with something where you've got a large amount of data translated and then synthesize it. And would that help? Would that work, or is that too much noise?
I think we have number of recent papers on direct translation models as well. So I think it could potentially improve the performance to further, So yeah, it could improve the performance if we use translated data.
Thanks.
But in Punjabi language, like we have like huge amount of unpaired data, but not the labeled data is not there. So we have a lot of interview data, news set data, but some of the data sets are very private and they don't have a huge amount of data, and some are owned by government. They don't really release it. So in from that perspective, it's kind of a low resource languages because we don't really have a targeted linguistic resources about that.
So I wasn't going to mention this idea, but now you've told me some characteristics of Punjabi.
Yeah.
The other thing I was wondering about when you were talking about speech augmentation is whether or not you could use a GAN model, right, to augment the
of
speech
course.
with indistinguishable speech. And in the case that you've got with the Punjabi, that seems like a particularly good situation for doing that, because you've got a large amount of adversarial examples.
Yeah, I think I totally agree with you because a lot of augmentation recently are based on cyclic GANs. So they try to, generate the samples and then discriminators and with the generator, they try to guess the examples, whether they are good enough or not. Yeah, I think this kind of augmentation can also be used. Yeah.
So very nice talk, very clear. And since you're in Auckland, it would be lovely if you would come over and give a talk to our lab at some point.
Sure.
Like redo this talk, for example. Okay. I think that would be fun.
Yeah, sure, no problem about that. Yeah, thank you very much for your comments. Any more questions, please?
Seth, thanks. Yeah, I also think it's a very good talk, and I might also invite you to do your talk again to my students, but unless you're too tired of it. I have some questions. We are collaborating together. I'm from Singapore. Now, what does it take if you, what do you need if we want to say, okay, include the other languages that we're interested in this project, specifically Malay, and Singlish, which is more like a mixed type of language. What would you need if you want to expand the scope of your Māori work and Punjabi work to these other languages?
I believe that you can add as many as language you want, but the only thing is like as I said in my talk as well, randomly adding the languages don't really help. The languages that are phonetically similar, the languages that share some common characteristics, tend to improve more as compared to the randomly, giving out languages using training multiple system. So in that case, it should be, we should do the case study, like what languages are very closely related to our target languages, so that we can create a subset of languages that, kind of used as a source languages to train our model. Say, for example, in my talk, I said like Māori language is very relatable to Japanese language. So it is a very good potential candidate for that. As a source language, we can use Japanese so that it can, share some phonetic structure while training a model, and then it can fine tune on a Māori language and can produce better results. Yeah.
Okay. Yeah. The other question I have is, it seems like ASR tends to look at the task in a so-called general scenario. Basically, you have made the utterance, a speech utterance, and try to convert to word, right? Whereas in a lot of the other NLP area, we are quite task specific. Particularly for this project, we are kind of focusing on QA, question answering. So in a sense, then you kind of have a constrained environment, right? You have, let's say, if you have a text-to-text, speech-to-speech QA, then there's also behind it, there's maybe a source document where the QA is referring to. Do you think there's interesting, are there work done on this, a more task-specific type of ASR, especially in particular applying to QA?
I'm not sure about QA, but we have very, subfields in speech processing, like speaker adaptation,
Yes.
Identifying the voice of a
Yeah.
speaker,
Yeah.
you know, different subset of these things, like emotion, getting emotion out of the speech signal, like
Yeah.
what kind of a speech it is. Is it an angry speech, or, you know, mellow speech, or whatever. I think I have to look into that.
Yeah.
I need to, you know,
Yeah.
see whether we have literature on that, like
Yeah.
question to question
Yeah. Yeah.
thing. But
Yeah.
in general, in speech recognition, as we talk, even if we talk about question and answering, I think we our focus should be on ASR system, because it's just like, you know, we are just translating the what we have just said, and then we are feeding that thing to the, you know, text to speech, and then understanding module, and so on.
Yeah.
So it's like, you know, kind of a first module in that overall structure.
Yeah.
But I would love to look into that, which can be directly used as, you know, immediate module instead of different modules.
Yeah. 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 I mean, you know, from let's say your phoneme, whatever your that to word, right? Then after that, there is a synthetic information, and people tend to say things more grammatical than just random words put together. I guess all this information you can put together, you know, add it into your model in a more kind of integrated approach. And then I suppose for QA, in that sense, actually, you have even additional information about the context of the text, right? That is around a particular document that people are looking at. So as input to the model, you, in addition to the utterance, to the audio, you also potentially have a document, right, as an input that can guide the deciphering of the audio signal. I thought that might be interesting. Anyway, just a thought. Yeah. Okay.
Cool. Thank you. Any more questions?
Yeah, I have a few questions. First, one about the talk. So what kind of labeling is actually needed? I'm not sure I understand that.
So the labeling is just like, say, for example, if I'm saying I am Satwinder Singh, so it is audio and the text version of that. So it's like, you know, audio plus their transcript.
Okay, but it's more like a parallel corpus rather than labeling, isn't it? You're not labeling tokens. You are putting in parallel the text with the sound. So it maybe it's a matter of granularity, and I guess that's my question.
Yeah. Because initially, when the traditional system were there, we tend to have a frame level labeling where each frame represented a different phoneme sequence. But with the CTC model, which is connectionist temporal network, so with the deep neural network, we tend to achieve you know, frame level automatically with the different deep learning structures.
Okay.
So yeah, so it's like that. So if you combine the labeled utterances together, so it becomes your corpus. Yeah.
And you mentioned phonetics. So there are, I mean, one way to look at what you're doing is also going from the recording to the phonetics, and the phonetics to the actual written text. Where the second phase can use lexicons and things like this, but I don't see this separation in your work. You seem to be going directly from the recording to the written text. Any thoughts on that?
Actually, the model that I discussed in earlier, the traditional model, they tend to have these separation. But the idea of that is that every model is, you know, optimized differently. So if there is error in one, it can cause error in every other module. Say, so the problems lies in different set of separations. But the deep neural network, as we speak, like there are transformer transformer models and wave-to-act models, they tend to end-to-end learn the system. So there is no separation between each and everything. It's just like, you know, mapping the audio signal to their corresponding transcript. So there is no evident, you know, structure that we are following. So that's sort of the idea of new systems. So directly end-to-end doing stuff.
It is, but then coming back to Michael's comments about selecting the features, etc., they are lost in translation, if I may use this pun. So you have no way in the architecture to clearly identify, whether this is a phonetic error or a spelling error or, grammatical
I think
features.
that can be solved using language model. So language model tend to, this kind of model is contextual model. So they are trained on huge amount of millions of utterances, text sentences. And then these are the model that are used to correct the spellings, pronunciation mistakes. Say, for example, somebody is saying messy with one S. If the language model can, could potentially correct that spelling, because a lot of English pronunciation are overlapping. So language model comes into that play when we have ambiguities in the language. So I think language model can surely improve the performance in that regard.
Okay. Two more questions quickly. So talking about the similarities between languages so that you can use one for the other.
Yep.
You're talking about phonetic similarities, is it? Then that should be easily identifiable by simple classification, right? If you got samples from the languages, you just try and find out which phonemes they are using, and you can probably classify that. I remember we were able to do that very effectively for the morphology of written text. Yeah. And I don't quite see any additional challenge except the manipulation of the audio files.
I think it's absolutely doable, because there are a lot of studies on these kind of phonetic similarities and other kind of stuff. So I read one paper which has like 100 massively multilingual model, and they have done a study on different categories of similarity. So it can be phonetic similarity, it can be language family similarity, or it can be geographical area. So languages from similar area. So I think it is doable, and there are some studies who have already done that. So even we can look into that as well.
Yeah, could you share those papers, that paper and maybe others to the mailing list?
I will definitely.
Okay. So the point for this project is that Maori and Malay are of the same family. And I don't know Maori, but just hearing some speakers here and there speaking Maori, I guess there's a high similarity, phonetically at least, and possibly even morphologically, grammatically, etc. So that leads to my last question. What do you think about accents, or sort of categories of accents or pronunciation for speakers? I'm thinking you were talking about languages in India, like Punjabi and so on. I suppose you have accents, so that could be a great place
we have 4 accent for Punjabi.
So have you tried to play with that, distinguish, train the different accents, or
as of now, I haven't, but it's not a big challenge, because as I was talking about meta learning, which is like adapting to new tasks. Say, for example, I train a model on one dialect, and if I have a very few examples of different dialects, then we can easily fine tune the model on new dialect, right? Okay. So that they can incorporate all those pronunciation deviations and other stuff. So I think it's easily doable, and a lot of work has been done in this area, which is called accent adaptation, using different concepts.
Yeah, but even accent identification could be part of the system. You do the translation and you say this is a northerner or southerner, or
So it's Stefan, like, every speech has a feature set, so we can classify different accents.
So Stefan, it's interesting that you brought that up, because I was saying in the chat to Satwinder that it would be good for him to talk with my student Aaron Keesing, who's actually working on emotion recognition across accent variations. So I think there's an opportunity for some synergy here, and maybe involving him a little bit in this work.
Yeah, sure, no problem.
Right.
Yeah.
So you gave a great talk, and the bad consequences, you have to give it again.
Yeah, sure, no problem.
Thank you. Thank you.
Thank you very much.
It is recorded, of course, so he can cop out that way.
True.
Thank you.
Do we have a transcript? Oh, sorry, that's a joke. Yeah.
We can use our trained model to get a transcript of this talk.
All right.
Yeah. Any more questions, guys?
A normal question is thank you, Satwinder.
Okay.
Let's talk.